y'all. It's Dr. Know-It-All. I am here with Dr. Scott Walter once again, who apparently is breaking the internet on Twitter right now, and with Herbert, Brighter with Herbert. If you haven't seen that video, I'll put a link to that in the description. You've got, what did you say? You had more than a Gibbs today. You beat a Gerber, and then you doubled your Gerber, and then you beat a Gibbs.
Yeah. So we know what a Gibbs is. It's something like 56K views, at least on Herbert's. So
yeah, on Herbert's thing. Yeah, it was my time on his channel. So you beat me on
so
that.
John, so as a result, I had to put on the right T-shirt today.
There you go. And that is available in the merch store.
In the merch store, exactly.
Apparently nobody gets that. We thought it was really funny, and everyone's like, what does being on an ego trip mean?
Even people from Tesla don't understand it. I have to explain to them what ego is. And it's like, ego's the car. It's the car.
It's from AI stuff. When you hear me talking about the release notes and they talk about ego cars, it's your car. Mm-hmm. Okay, so I want to start today. We're going to talk about Optimus, but I want to start with your tweet, just the main one. We're just going to really quickly touch on that and then go to a picture, because you discovered something really interesting and fascinating from the video. There are so many Easter eggs in there.
I keep on finding things. Yep.
I know. So let us begin with sharing. All right, there we go. So I'm going to start with this. You can read this as you want, but basically this has, I think I just looked this up, and it has, where is that? Somewhere down here. 141,000 views. There we go. So anyway, This has become quite the popular tweet, and it's also part of a thread. So we're going to talk more about that in a minute. Anyway, Optimus will obliterate the factory floor landscape, and you should read this.
Oh, you wanted my voice? Okay.
Yeah, it's your quote. So there you go.
All right. Optimus will obliterate the factory floor landscape. When you give an engineer, a designer, or an artist a new medium to work with, they will always surprise you and produce unforeseen results. Just look at how mobile robots revolutionized the Amazon warehouse. Optimus is a new medium for factory designers. At first, it looked like a one-to-one swap out of labor, but it is more, much more. The factory space will be radically altered. Optimus opens up a new possibilities frontier. Cells will be more compact, processes will be eliminated, because the rules have changed. No more cages, no more barriers, no more intermediate steps. Just look at the Tesla Shanghai speed video to see how crazy the status quo currently is. A human operator loads parts into a preloader or pre-feeder that feeds a robot that finally feeds the part into the robot production cell where the work is done. It is a bucket brigade of handoffs, of middlemen, of extra processes, of extra resources, lost cycle time, lost floor space, unnecessary handoff fixtures, complex end-of-arm tooling, larger robot. It is inefficient. There is no value add in any of these extra steps or capital equipment. The reason is safety. Operators are feeding Phoenix at the robot zoo. It is too dangerous for a human to enter a robotic work cell in operation. But Optimus can. Optimus can do a choreography with the industrial robots, which will endanger neither it nor the industrial robots. It will direct feed the process because it can. Dark Optimus will dispatch that problem. Welcome to the new industrial canvas. And you can show the image underneath of Dark
Yes, let's see the
Optimus.
image here. There we go.
Yes. And all right, shout out. Okay, first, shout out to Ellie Sharif of Ellie in Space, because she reminded me that tweets get more engagement if there's an image associated with it or some sort of meme. And so I said, okay, I'll just go ahead and put it in there. And the other reason I put this out was that on Pi Day, which was the 14th, Herbert and I had the interview, but it wasn't going to be released until Sunday.
Right.
And so these were just kind of being released out there before that one to get a little bit of interest in what was going on. And it seems to have done the trick. Right. One of the first tweets I put out there earlier was in Herbert's interview. It occurred to me that the operation that we saw at AI Day 2, where Bumblebee was picking up a part and then putting it in the red tray, was like, that was clearly in the factory floor. It wasn't in a laboratory setting. It was like, holy cow, I bet that part is actually in a Tesla today. So Optimus actually touched a part that made it into a vehicle. And so it's like, oh, the robots are coming.
Right.
And so that was the first thing. And
the
and
robots
this
are
was,
here.
right. They're here now. Now the thing is, I do not have a good enough imagination to really know how it's going to change the landscape. I just know it is.
Right.
And it's really interesting to look at the comments and everything else, the engagement, all the ideas that people are having. It's been a really nice discussion. In many ways, it's helped me shape my thoughts and ideas of what's going to be going on here. So I really encourage people to, continue to do that, to, to give us your ideas and your thoughts. They're well appreciated.
Yeah. And I think it's worth pointing out that one of the things about the future is that, even Tesla doesn't know exactly how this robot might be used, right? When Steve Jobs introduced ye old iPhone in 2007, he had an idea, but there's stuff that it does now that even he wouldn't have understood, right?
He
was
no
a
idea.
genius with this
Right,
stuff. Yeah.
Right.
So,
now this image here is from the Shanghai video. And that's the preloader station I'm talking about.
Right.
Is that down there, 2 parts are placed there and the robot comes up and picks it up. And it just seems kind of silly. So, an operator is taking something out of a bin, bringing it over, dropping it there. And now the robot picks it up and then it brings it over to where it's actually going to have the process done. So now Optimus can do that job already. So we can already replace the operator. But the question is, why is that operation even there anyways if we've got Optimus? This is going to change everything. It's going to move it around. That robot will not be needed. That end of arm tooling will not be needed. That silly fixture is down there will not be needed. That barrier we see around there will not be needed. Right. That floor space will be gone. So you begin to see those things. And now just imagine, like we say, you give an artist, a designer, an engineer, a new medium to work with. What are they going to do with it? I have no idea.
Right. So I want to continue with the big picture stuff because this is actually super exciting. And I think the idea of safety and stuff is really important. But you also noticed something. This is kind of a blow up. Let me see if I can reduce this for a moment. So this is
a second. One last point on that last one is if we just go back to that, a lot of people have asked, well, I mean, why don't they just have the normal robots do that? Why isn't it automated? And it's a really good question. Why are the humans there? Why has it not already been automated?
Right.
I have a tweet thread for that.
Okay.
That's a different video, but you go around there and I really go in a lot of details on why it hasn't been automated today. Right. And that will give you an idea why Optimus is the better solution than saying, well, why don't you just bring the orange or yellow robots out there to do that in the first place?
And I think that's the critical part. That's the critical part is where does
understanding. And there's a lot of points.
Obviously are places where the big yellow robots are, they make sense because
they make sense. They make sense. They make sense. The bottom line is the bottom line, and that is ROI is king. All right.
There you go. Okay. So this is a still frame from the Optimus operation video, whatever. What'd you call it? The Steve Optimus? Like Steve
Optimus, where the operation that's going on there. And I'd seen this before and I just noticed the ribs and it just didn't occur to me what it was. And the reason why I did it, and again, this is why comments are so good, because we've been having a discussion, and this will be another video of what is the charging plug going to look like. Yes. Is it going to be the NACS adapter or is it going to be something else? So that is something. And I was thinking, I wonder if I can find it in there. I wonder if somewhere we can see where the charging port is. And then I looked a bit closer and I realized, oh, those aren't ribs. Those are 4860s, 4680s. They're 4680s. Right. They're absolutely 4680s. And I can see it on the other side. So that's our batteries. And so, John, how many can you count? So
so just for people who aren't paying attention here or might not be able, if you're listening to this and not watching it, we're looking at the robot that's on the table, which has a lot of its outer protective coating off, like the plates and things. So you can see inside, and what obviously looks like 4680 battery cans. There is, as far as I can tell, there's 8 of them stacked vertically on the left-hand side.
There might be more. It's hard to tell, but 8 for sure. It could be 9, maybe 10, but let's go with 8.
Right. So anyway, and then you did the approximation that if these things are approximately 0.1 kilowatt hours per battery, which is a little bit aggressive, but that you would need or around 24-ish batteries to make the 2.3 kilowatt hour battery pack.
Right. So, exactly. So the question is how many are there? The question is, how many do they need? Right. So it's clear. We're looking at it. It's 4680s. It's not 2170s. It's 4680s for sure. And from that, we can surmise that, well, there must be somewhere between 23 and 24. So since it's not quite 100 kilowatt hours per battery is just a little bit shy. Oh, you throw another one in there.
100 watt hours. just to be
100 watt hours. Yeah, 100 watt hours per battery. That means if it's a little bit shy of that, gives you 24. 24 is the number that's nicely divisible by 8. Now, I don't think you have 8 columns going across there. I think what you have is you've got 1 on each side. So you've got the outer rib cage, and you have maybe, 4 down at the bottom and 4 at the top. So it makes a big circle around it. And why would you want to do that? Why would you have them all on the outside?
Yeah. So, I mean, so what we're looking at is like a rectangle that's imagined, of course. This is speculation. We haven't seen the back of the robot. But
interesting enough. Yep.
Yeah. But number one is that it would allow for other mechanisms to be shoved inside of it if need be. Also, cooling is much easier if you don't have multiple batteries stacked up next to each other. There's a much easier air cool, because remember, this guy's not going to be liquid cooled almost definitely. So it's going to need to have access to air and air running over it. So you could even put something like a fin back there, like what do they call it? The thing on top of your CPU, the little radiating fin, right? Where you blow air across the top of it or something. So,
heat exchanger,
things like that. Yeah.
But you won't need a heat exchanger because it looks like the external parts of the batteries are exposed.
Right.
It's only consuming between 100 and 500 watts. So maybe, the heat that's being generated will be sufficient to be able to be transpirated or radiated from there easy enough without having any special, cooling fins or any other mechanism, because it's external. There's nothing internal.
Right.
Yeah. So that's our guess.
Kind of genius, because originally, of course, I thought they would just smash them all together and make a box.
I did too. That's what I thought.
And in fact, I think actually, if we went back and looked at the AI Day #1 videos, they actually had like a box that had the hardware for essentially the hardware for half of one, plus all the batteries in one box. But they may have decided that was just too hot.
And I don't know if this means whether the pack is swappable. How easy it would be to be able to pull that out and put another one in.
Boy,
because it's a big ring.
It doesn't look like in this version it's very easy.
Right. Now, it might be easy to get the individual batteries and, kind of pull them out. But I think the whole idea of the pack being able to do an exchange, which is why I thought that they're just going to charge it. They're not going to have a swappable battery pack.
Yeah.
And my feeling was because, parts and processes and all that, you just, you don't need it. You're going to just,
again, there was, do you remember the argument back when these phones first came out? There was several Android makers specifically that were just stuck to their guns. Like, we need swappable batteries. And eventually that died because all those extra parts and things are just way more parts for failure. When you have a block, it's a block and it's very difficult to break it. But when you have little plastic doodads and stuff like that, connecting things just as easy to break. So
yes. And they could make it more part of the structure. There's a variety of reasons you do not want to make it swappable.
Right. And especially with a relatively fast charger, these guys are small battery packs. They should be able to charge in a couple of hours, and probably
quicker than that.
Probably 10 minutes to get a reasonable amount of charge. So, we're looking at a small amount of time. It's always that last little bit takes forever. So a couple of hours is a hyperbole. We're probably looking at 45 minutes to go from 0 to 100%, but 10 minutes to go from 10% to 80 or 90%. So
yes, I agree, because it's going to be DC. It's not going to be AC.
Right.
We already know with a 350 kilowatt hour supercharger and, your 70 watt Model Y, what you can almost top it off in 45 minutes or something like that.
Right.
And this is 2, not 70. So it's like you're talking about a factor of 35. Now, it's not as easy as just saying, take the time and divide by 35, because you get the charging curve, you get chemistry, you get everything else. But it's not going to be the same as trying to charge up a Model Y.
Yeah.
It's going to be a lot quicker. And so I really think it's the time between a shift, because there's generally about a half hour between a shift.
Wait, do they give the people a 15-minute smoke break so Optimus can just take a 15-minute charge break?
Yeah. And these other theories that you may be able to have charging in situ at certain workstations. So if you have a very sedentary process where Optimus does not have to walk, then it could be charged during that time. And you may have others that are walking around. And then once the sedentary one is like charged up, he can go over to the ones that are walking around and tap them on the shoulder and say, I'll take over. And then the other one walks over and does his job. So there's a way of doing that, of just kind of.
Oh, that's true. You could round robin.
Yes.
Yeah.
Yes, exactly. So, and Tesla solves a lot of hardware problems with a software solution. So that's a kind of software solution, is you just go around the merry-go-round. You don't have to charge them all at the same time.
And I want to show this guy on the right here, or well, I guess they're on their right. But anyway, so you can see this is all exposed, and now you can see the plating on the outside. So the guess would be that this would be some sort of a metal frame that was put on the outside that radiatively cools it because it's in contact with the batteries.
Yes,
and it protects them so you don't bash your hands against it or shock yourself or do something stupid like that. So
yes,
to make it reasonable.
So that's it's and if you look at the video, you'll get little glimpses of it every now and then. So sometimes it stands out more when you get the motion because everything's a little bit blurry when it's freeze framed. But when it's moving, it's like it really comes into focus and go, whoa, what's that? And you go back and you play it again and again.
Right. Unless you're Dan O'Dowd, in which case you're doing 240p video. So
yeah,
it just if this was something from the Dawn project, we would maybe be able to see that it was a humanoid looking form there. So
right.
Okay, so that was a great discovery, and I think that's pretty fantastic. So let's turn back to this, and I think let's just talk about. The reason is safety. So let's start with that idea. I think that perhaps is the crux of what you're talking about here. So, okay, so for people who don't know, let's go to a factory that has a Fanuc or a KUKA robot or something like that in it, and you've got a human being who has to interact with that robot. What has to happen to make that happen?
Well, there has to be a barrier between them.
Okay.
So
and the reason
when the cell is in operation, absolutely no one is allowed in the cell when it's operating. They have to be outside in the safety fencing area. Yes, exactly. And they make all kinds of precautions to make sure it cannot accidentally happen. Okay. So they will have physical barriers, they will have light sensors and everything else. And when the operator loads the robot, he has to stand back, I think, at least 1 or 2 meters. Okay. And he's behind a light curtain. And if he breaks that light curtain, and you will see in the Shanghai video that he accidentally enters the cell too quickly and the robot stops and he has to restart it. And that distance is there because if someone takes a running leap and tries to like jump into the cell when the robot is moving, the robot has to be able to stop in the time that he's able to run that distance. So that's why they have to stand off. That's the safety margin that's there if the light fence is broken in any way.
And then beyond that, you could see, of course, there are cages and stuff. So there's physical barriers too.
There's physical barriers. There's all sorts of things. Now, people always figure out how to defeat it, but it's very, very hard to do it. So there's a huge distance, and you'll see when they are doing the tour, you cannot really see the robots up close because you cannot get there. Partly because they are big and they're moving fast, and they've got end of arm tooling that's got all sorts of pointy, sharp things on it, and it's not soft. You can easily be killed if you're hit with one of these things. And then the operations themselves, if you're doing arc welding or something else, you don't want to be that close to it as well. So you need to keep people far enough away from that. That eats up floor space. I mean, look at the floor space you have there just for the barrier. I mean, it is a frontier, or it's like a border between two countries. You know, there's like this demilitarized zone that you have between the robots and the factory floor. And I've referred to this as the automation event horizon. You know, it's like you don't want to go through it because you can get consumed. And the problem is if you start adding more automation, your black hole gets bigger, your event horizon goes out and it starts, you know, consuming and eating up a lot more of your factory floor. And you would like to be able to get rid of that. Now, the only time the humans are allowed in there.
You could add in a complexity of process too, because let's say you had 3 robots that needed to deal with things, but in between those robots, you needed to have a person come in and put in a part or move something. Then suddenly you're looking at ridiculous things. You've got choreography that has to happen where one robot does it, then it stops.
There's a lot of that.
The person goes in, then they move out of the way, then the other robot.
That happens. And that will happen. The robot will kind of take it and then move it over here and bring it over to somewhere else where it needs to be fed. So the example I've always used is like, you know, feeding the KUKAs at the robot zoo. So if you go to the zoo, you know, how are the lions fed? Well, they have all this caging and everything else and slots that you open things up to slide the trays in with the food to make sure there's no interaction between the two. So the same thing is going on here. And unfortunately, the human operator, you know, the question is why can't they automate that step? And that's because they have these big bins just full of the sheet metal parts that were pressed like, you know, a day or two before and stacked up. and just kind of randomly in there, and you just have to pick them out. And the human operator is pretty good at just being able to go in and grab a part and grab another and bring it over and drop it over there. They really can't screw that up. And it's a very easy kind of process. And now the robot can pick it up. But now that it's in a known location, that robot can come over and pick it up and basically ferry it over to its final destination. Right. The human cannot get it to its final destination. So that's why I say there's this handoff that's going on that is very inefficient and slows things down.
Yeah.
Would be nice to eliminate that. Now, Optimus can go right on in there, can walk around, knows when to duck his head when the robot's going to be coming on over, and is able to directly feed the process. So that's just one example. I mean, I'm spitballing on what it can do. And that's like, already, I see that as an example.
Right. I just kind of love the idea. I think you said choreography someplace. Yeah.
Yes.
Do a choreography because it literally knows when in the cycle time, the robot arm is going to swing across, can duck under it if need be. Now, I don't know if Tesla would go to that extent because they probably don't want to break their Optimus.
You don't necessarily have to do it, but you know the dance steps. Let's look that way. Okay. Yeah. So you kind of know that this is the path I have to do. I have to be there at a certain amount of time. It's getting all of the information from the robot cell real time, where the robots are and when it's safe to move in. It doesn't have to guess. And it's just a repetitive process. It just goes over and does it again and again and again.
Right. And that's another thing is that human beings are really, really bad at exactly repeating the same thing over and over again with the same timing and the same steps.
So they can do it, but not for 8 hours.
Yes, exactly. Exactly.
All it takes is one mistake.
Yeah. Yeah.
That's it. Your cell phone goes off. You're down there, you're distracted. Yeah.
Yeah. If somebody damages the Optimus, it's not the end of the world. If somebody damages a human, that's a bad day. So
yes, that's a really bad day. So now what you can do is you can start moving the material closer to where it needs to be operated on. And you are getting rid of these robots that are moving from one station to another, all this stuff. So already you are saving money. And at first we thought the saving is going to be in the labor. Right. It's all going to be about OpEx. What we're looking at right there is a CapEx savings.
Yeah.
So
that's true.
It's like,
I mean, even if you could shrink the factory floor size by 10%, that's a huge CapEx savings.
Yes, absolutely. And now that's floor space you can use for something else.
Right.
Yeah.
Cool. And of course, a process savings as well, because you don't have to have that waiting time and the barriers and all of those other things. So there's a huge amount of stuff.
Yes. Yeah. Some of that might be slowing it down as well. So you might be able to get a faster throughput for sure.
Right. Yeah. So, I mean, that's kind of the critical thing here is that I think people, let's go back to, I was going to say that I know there was a question we started with, which was why use Optimus shaped robots rather than just making another Fanuc or KUKA robot. Like, what is the advantage of these robots? Why not just have another robot that picks the thing up and moves it over there for the other machine to ferry over?
Because at some point you need a humanoid type of form to go and grab the parts out of the bin. It's as simple as that. It's the way the part flow is set up right now.
Yeah.
It's really sort of designed that at some point a human operator has to start feeding it the steaks or whatever you want to think of it and grabbing it out of there. And it's not as easy as like we just shove this big part spin up in front of it and then have some robot kind of picking it out there. And it really comes down to like return on investment. And again, when you set up a cell like that, you are taking that automation event horizon and then making it grow out a little bit more. And once again, we're just moving the barrier a little bit further here and changing it. The bottom line is if it was really easy to automate, they already would have done it. They already would have used the traditional robots to be able to do it, and they haven't been able to do that yet. And it has to do with the way the material flows through. And if you want to think about where the sheet metal parts come from, that's kind of a discussion. If you want to go down that rabbit hole, we can.
Well, I mean, we can take perhaps a slightly more general tack on that, which is that some things you can place in a little thing with markers on it and it fits right in there. And then the robot knows it's there and it knows exactly where to pick it up. The robots are dumb. They don't really have a bunch of sensing. They don't have a way of understanding the environment. If it reaches over there and it's not where it expects it to be, it may be able to shift around a few millimeters, but it's not It's not going to understand.
It wants it to be exactly there. And,
Yeah.
and the problem is when you have parts that are just in a big box, and it's really in a big box, and they're randomly in there, you will need some sort of vision system or something in there. Go ahead and find one for it to be able to figure it out, go down and grab it and bring it over and then load it somewhere else. And then also you got to think about kind of the volume requirement there. Is that robot's going to have to work kind of big, because you'll see there's a certain amount of movement, and the dunnage that you have with all these things is pretty big. So you just can't do it with a tiny little cobot. You need something that's able to reach down there and get everything. And these things are just brought in with a forklift and dropped off wherever. So then you have to say, oh, okay, how do we set it up to be able to do it in precision? And I've seen a couple examples where they've automated something like that, but it's just costly in the end.
Right.
And it's easier to go ahead and do it with the human operators. And now if you have generally is more of a general purpose kind of humanoid robot, you'll be able to do it like that without even having to change the layout. Right. So the first thing is you don't have to change anything. And the second thing is like, well, I said you don't have to change anything, but now we're thinking maybe we do want to change things.
Right. So it's kind of a two-step process here. The first one is to substitute out the human labor for Optimus and get it to operate as well as a human. And then once it's doing that, it's like, well, what can we do now that we couldn't do with a human being? So there's kind of a two-step thing that's going on here. So
yes, that's going on there. You can swap it out. And then I've had my mind focused a little bit today.
Right.
I want to thank Amy for this. She's sort of like asking me to write down some thoughts and stuff like that. And I'm beginning to realize that I think I know better what Optimus is going to do, where the first production line is going to be, and what the model is going to go in there.
Really?
So yeah. It's starting to become clear. So the first thing is we have the low-hanging fruit, which from now on, I'm not calling low-hanging fruit because everyone's tired of that analogy.
Right.
I'm calling them strawberries. We're picking strawberries because strawberries are the ultimate low-hanging fruit. They're on the ground, right? And so we're now looking for strawberry fields forever here. All right. So the strawberry fields is the loading process that we've been seeing in Shanghai. And there's lots of those for like the underbody and everything else that you need to have for a car. The problem is the gigacasting got rid of all those robots and all those processes. So I like racking my brains like, oh my God, it's like the low hanging fruit is gone. You know, they went in and they replaced it with the giga, you know, where are going to be those processes that are going to be there? And I was like, well, okay, Fremont is making the Model 3 and they don't have the castings everywhere. So there'll be a little bit that's there. And I thought, well, wait, no. There are two models that do not use the gigacasting. What are they?
Oh, the S and the X.
And where are they made?
They're made in Fremont.
And only Fremont, exclusively Fremont, right? So it's and what's the volume? How many are they making?
They're small volume, so it's really
they're not making a whole lot. They're not making a whole lot. So what if you take down the line for a day or two?
Right.
It's not really going to impact the bottom line.
Yeah.
They're doing it now. It's like SNX is being automated by Optimus as we speak. That is my prediction.
If you just purchased a Model S or Model X with a very recent VIN, there's a chance that it has parts in it that were touched by Optimus.
Yeah.
That's cool.
Yeah. Or will be pretty soon. Yeah. And so if you see anything like, oh yeah, the SNX line was down for like 2 weeks here or something like that, it's like, right there. Yeah, we know. That's when they get the change.
Swapping it out.
But I think it's going to be, I mean, it shouldn't really affect anything ideally because it's going to be a one-to-one swap.
Yeah.
That, okay, we've gone in here, and like I say, a lot of the stuff they can test out on like the third shift or the fourth shift or something like that.
Right.
There's no leaks coming out there. So they're doing a pretty good job keeping this under wraps, whatever. And then they will be ready. And my prediction is that they're going to show it on that line, proof of concept, and then they'll be ready to deploy somewhere else. And of course, they're trying to go for the tougher processes, you know, the assembly line and everything else. Because if you look at the assembly line, again, if it was so easy on the final assembly to automate all those steps, they would have a long time ago.
Right.
You know, body white is done, the painting is done. Final assembly, no, we need the humanoid form factor to do it. So that answers the question, why do we still need a robot like Optimus? Like, because we can't figure out how to do the final assembly line.
Right. and part of that may honestly just be the fact that a car is built for human beings to get inside of. So,
yeah.
so a person can go sit in the seat and mess around with the dashboard and, fiddle with the bits and put all the things on that are needed to go on. So, yeah. So you've got something that's already designed for humans to be in. So that is really fascinating to think that the S and the X are the low hanging fruit in terms of the model of car, because they are low volume. I believe they already do a lot of experimentation with those to kind of proof of concept different.
Checks all the boxes, everything that you need to get it out there at first.
And they don't use gigacastings either, right? So
exactly. That's it. They have all these small little feeder processes that they have to do today anyway.
Right.
And so you can go ahead and do it. Whether Optimus pays for itself because the volume is slow and everything else at this point, it doesn't matter, but it's a really good proof of concept to be able to go through.
Okay. And this goes back to that whole ROI thing too, because if you think about it, the reason why Model S and Model X don't have gigacastings is they don't make enough to make the money back. They're extremely expensive to get built and set up and everything. And you want to produce like 1 million cars. You don't want to produce 10,000 or 15,000 of these vehicles.
Yes. So the volume is not there. So I'm not sure what the break even was for it, but it was a couple 100,000 a year, I think, is when the gigacasting starts to make sense.
Right. So you're looking at cars that are order of magnitude too small to make sense to do gigacastings, but that's perfect for Optimus. And then I think the other thing that you had talked to me just before we started recording was the advanced planning. So the robot, obviously it uses full self-driving technology to sense the world and to understand it. And we looked at that in the occupancy networks. But then I think you were specifically talking about in the video where it flips the one hand over and does look like it's playing the violin.
Yeah.
It's like planning out its moves.
Right. So, FSD, you're driving down a three-lane road, and there's a left turn coming up and you're in the right-hand lane. What do? At some point you get over in the left lane before you have to make the left turn. And so FSD is sort of thinking about, in the advance, what should I be doing? And if I'm taking a right turn, I've got a quick left turn. When I'm done with that, where should I get? And if you remember in the video, I don't know if we want to bring it up, but he's coming over to grab the part. And at one point, rather than, grabbing them, one hand is from the top and one is clearly coming from underneath.
Right.
And it's almost like this decision was made as an approach, like, oh, no, I don't want to grab it from the top. I want to grab it underneath. And the reason why I wanted to grab it underneath is if you then look at the next step, or actually maybe 2 steps after that, it brings the arm over to Steve Optimus to put it on the right shoulder. And it just makes sense that it's being grasped that way. Otherwise, it's going to come in the wrong orientation.
Yeah. I don't recall.
So it's kind of looking ahead. So if you think about it, that's what an operator would do. Once they learn a task, you always think about what's the best way to grab something so that when I go to the next one, I don't have to set it down and then readjust my hands or anything like that. So already it had a decision, grab from the top, grab from the bottom. And it made more sense from the advanced planning standpoint to grab from underneath.
I think I've got us to the correct point. Oh yeah. Look at me.
Yes.
Come I remember where this is now.
Yep.
So it's right at the beginning of this video. So it's this moment here. It does the unplug.
Pulls that out, right? And that there, it already changes trajectory. Then it's there. It's thinking about, I'm going to grab it. It's like, oh, no, I want to come underneath now. Grab it underneath because it makes more sense for the process step that's going to be coming up.
Right. So let me go back. So it just unplugged this and just watch the left hand goes, it thinks about it. And then it goes, I'm going to do this.
It hesitates for a second. It's like, oh no, that's not how I'm supposed to do this.
It is possible that this is choreographed, right? Tesla might have pre-programmed this, but this is the kind of thing that the robot should be able to handle. This is like full self-driving where you have to figure out the best method possible. We don't know, but anyway,
so
you can see it
there's like,
looks
no, going underneath. Got it. Now, why would you want to have the hand grip there? So when we go ahead, after it's brought over, starts
and that
walking.
was really pretty, by the way. I love the way that the fingers kind of fold up that way. So
looks very nice. Yes. So now the steps are going to come in here, and that is exactly the orientation you need the hand to be in order to have that arm. Now the next thing I want you to see is,
and here you can see the batteries again.
The batteries really well. You can count them very easily.
Oh, and actually, there are heat sinks right there in the front of it. You can see those clearly. So which
could be, it's either for the batteries or it's for the computer. Who knows?
Right.
Could be for both.
Or both. So
Now it goes from two-handed to a one-handed grip here. So suddenly it's going to release it.
I don't recall the cut between these two.
Yeah. So, okay.
Oh
So
yeah,
at that point, you see
it's
it's
sort
one
of
hand.
magically gotten rid of the one hand
Yeah,
there.
we
between
didn't
cuts.
see that because of the editing cut, but now
Right.
it's in one hand, and you see that the orientation of the hand makes sense. So it's from
Oh
there,
yeah, you're right.
and it
Oh
switches
man,
over.
so that's not just planning ahead. That's planning ahead a long ways because it's like, what's the easiest way for me to hold this to hand it off? So
Yes, exactly. So it did not have to do anything else. It just went from two hands to one hand. I'm
right.
estimating that weighs, I think, around 15 pounds or so, that hand.
Okay.
And that's an extended grip. So arm extended payload. And according to the original specs, that was around 10 pounds. And that's like an
Right.
arm extended, and it's holding probably around 15 pounds.
Right.
And I was able to do a spreadsheet to guesstimate how much Optimus weighs right now, because they told us how much all of the servos weigh. So from that,
okay.
I was able to add them up, and then, try to guess how much the battery. Now I can probably do with the battery pack, because I think I know how many batteries are in there and put that in there. I was looking at the weight to try to figure that out. So I've got some guesstimates, and it's coming in maybe just right around what they were saying, around 125 pounds. It might be there or just a little bit heavier, but it's very close to the spec.
I love the fact that it's got the little shotgun thing.
Yeah. So, that's, and I wanted to figure out how much could the arm weigh. So that's why I added all those things up to get some sort of guesstimate, to get an idea of what the payload capability was with a one-hand grip.
Yeah. So, but I mean, I hadn't even thought about that. So you weren't just talking about instantaneous planning of thinking like, oh, I need to pick it up like this. It was actually going like, if I'm going to hand this off eventually, I need to hand it off. That's the best way to grab it. I can't hand it off like this.
No, so, that was the wrong way. That's the wrong way. Yeah.
That's fascinating if it's thinking ahead that far. And again, we don't know at this point in the process. It's very possible that it was given very explicit instructions like flip your hand upside down, pick it up, let go with this hand, so it's possible that it's much more choreographed and scripted right now than it will be eventually. But it still indicates a pretty solid understanding of the universe to be able to understand these objects, where they are, how to move them, all of that kind of stuff.
Right. And, it may be that it's looking at it saying, oh, that's a right arm.
Yeah.
And I need to bring it over the right side, and I need to grab it this way. And if that was a left arm on there, it may have taken a completely different strategy, or decided, oh, I need to actually kind of have it with this hand to bring it on over there. So who knows what it would have done.
Right. Interesting. So yeah, so again, I think hopefully we put that whole original thing to bed, that this was like somehow CG, it was computer graphics. It's not, it's real. We don't know exactly how much of this was, obviously it was all advanced planned, but how minutely it was planned. I mean, there's the difference between me telling you, Scott, go pick up the arm, bring it over here and stick it in the slot so I can screw it in. That's one level. That's very gross. And then to break it down into like, move over here, rotate your arm at this amount, move forward, 10 degrees with this joint and 15 degrees. That's incredibly granular. So
it gets kind of granular where everything gets broken down, just like FSD at some point says, how much pedal application, how much do I need to turn the wheel? So you will probably have this high level task that's like that. We need to turn the socket, so we need a tool for it. So it knows, I need a tool. Look for a tool. So it's like, let's find a tool, and then it sees the tool and knows, I now have to go grasp that tool. That's the location of the tool. Go down there and get it, and then it knows already. The tool does have a trigger, right? It has to turn it on and off, and so when it grabbed it, it made sure one finger was out. After it grasped it, so it would then be able to go up and then apply the pressure onto the trigger to be able to get it to work. That's also going to be interesting, because Joe Munaretto had talked about, the app that carrying a load is going to affect your walking. So walking is easy. And then as soon as you carry a load, whoa, that's going to change everything, going to balance. And I realized, when you get a tool like that, you also have to worry about torquing and reaction forces. So when it goes up there and it puts it on there, puts it on really hard, it's going to, it's going to have to kind of say, whoa, I've got to get my hand back. So it's going to begin to understand how that feels and what it needs to do. So that's going to be rather interesting to see how it's able to deal with reaction forces and torques.
Right. And it seemed to handle that pretty well. I mean, I'm sure we humans, if you've ever been like screwing something into a piece of wood and it catches a knot or something, and all of a sudden there's resistance. You go like, woo, and your hand pops.
And then whoa,
because,
and that's an indicator something's wrong and it sounds wrong. So there's going to be this feedback loop where it's going to know, whoa, there's something wrong here. And maybe it does a quality check flag. Either it looks at it or then says,
right,
okay, I kind of faulted here. Get the human to come over and take a look.
Right. But there is, what you're describing when you break down how complex what this thing did in the video is, the number of steps would order in the hundreds, probably, if you really start breaking this down. And the question is, there's some level between defining every single particular movement, which is completely choreographed, like what they do with Atlas, with Boston Dynamics, and me saying, Optimus, go over there, pick up that arm and bring it over here so I can screw it in. There's a range of different granularity. And the question is, how detailed did they have to get? Were they able to just do it in like 4 or 5 major pieces, or did they have to break it down into multiple subsections? We don't know. That's just something we can't.
Right. So they probably have these almost macros that are already set up to say, this is a grasping macro, or this is what you do when you grab, and then it starts to learn to grab different kinds of objects. And then at some point you can describe it at a very high level language, and then it's able to break it down. And then, the neural networks do their magic to sort of figure that out of like, oh, we're looking for something that looks like a socket wrench. Where is it? A power wrench. It's going to be here somewhere. Oh, normally it's orange. It's about the right shape. It's over there. I'll go ahead and grab it. Right. And then it knows something about it and how to operate it. Yeah. So it's obviously being taught a library of those things. Right. And how they do it, that's what I'd like to find out. And that's kind of their secret sauce right now.
Somebody at Tesla, please come give us a tour. We promise to be quiet about it if you give us a tour. But yeah, I mean, that's where the real secret sauce is. It's like, but again, for people who doubt this is so much easier than full self-driving. The balancing, the walking, the mechanics are much more complicated, like the output controls, but the input controls, it's like you can refine this to just a drill, just that vertical thing, just the watering pitcher, just an arm. There's just a few things it has to understand in the world. It doesn't have to understand literally everything.
But there is a little difference. The whole idea of full self-driving is to navigate through the world. Right. It's not to interact with it. True. Let's be clear. True. We're not interacting with the world here. We're just navigating
the opposite of interacting.
And Optimus has to interact. Right. So there's a completely different kind of set of instructions and things it needs to do. So it does need to navigate, but it's not as a challenging a navigation. But now it has this completely different set of things it has to do, and that is actually interact with the world and understand how the world is going. So yeah, 2 different problem sets there. Yeah. But one of them, even though that one might seem more complex, it's much simpler because we're able to kind of keep it in a geofence, if you want to think of it that way, within a certain environment to make sure it's done safely and correctly. Yeah. And I'm sure there's going to be L1, L2, L3 kind of standards for humanoid robots. And they have to do some things to make it a bit more like a cobot, so it doesn't have so many sharp edges.
Oh, I was going to say, okay, so I have to go because I have to teach class in just a few minutes. But before we go, I think some people are a little confused what a cobot is. So, if you could just explain that, you've got your big Kukas and Fanics, which are the, the Terminator things, like when you go back to the original Terminator and you have these giant machines that are flipping around.
We have to be careful. When we say a robot, it's like a very all-encompassing thing. And you say it to some people and they think a C-3PO, and other people will say, oh, no, I'm thinking of like the Kuka robot or the Fanic. So you want to be very clear when I said the robots are coming, or when Farzad says that, he's really talking about the humanoid form kind of robots, because industrial robots have been around for a long time. And all those big robots that move very, very fast, and they're very, very deadly, and you don't want to go anywhere near them. So then there's this new brand of robots, which are called Cobots, which means collaborative robots that can work side by side with a human. They are smaller, they have a lower payload, they go a lot slower. And if they bump into you, they won't hurt because they're very round, and some of them are actually very, very soft. And they also have like a force feedback that if they feel something that's not right, they will stop immediately. And if it does bump into you, you can actually push it out of the way very easily. An industrial robot, if it stops, it breaks right there. And there have the last 2 fatalities as a result of industrial robots was operators being pinned. They couldn't get the robot off of them. It wasn't because they were struck by it. So the whole idea of a cobot is you can't do it. The other thing is making sure there's no pinch points in the cobot, because obviously if your arm comes down like that, it'll be like a nutcracker if you're in there. So they also make sure that you can't get a finger or something like that. So that's why they have these weird offsets to make sure you don't have any pinch points like that. Optimus may not have that problem because its elbow can only go down about like that. It can't go down that far. The same thing with its knee. It's still going to need some sort of covering, but part of it is payload and speed. The fact that it has two modes of operation. If an operator is close by, it goes at a really slow speed. And then if our operator is far enough away, it's not around there, it'll go a little bit faster, but it can't go super fast and it can't do a really heavy payload. So that's what kind of prevents the cobots from coming outside and picking up some of these parts, because you can't make them too big because then their payload will be too much. So it's kind of for small areas on those cobots. And there are standards there on what defines a cobot and what doesn't.
And we can go all the way back to AI day number 1, where Elon talked about that. He's like, you'll be able to outrun it if you can walk fast, basically. It weighs a small enough amount that you could push it over yourself. So you're going to win the fight if it comes down to it.
Yeah. And that's the other thing to point out is that in some ways, the cobots do almost have a kind of very springiness in their joints. So it's very easy for you to push them out of the way. If it's on you. But Optimus, you may not be able to do that. If it's arm there and you go to push its arm, you may not be able to get it to move. But you know what? You don't have to, because the difference between Optimus and a cobot and industrial robots and cobots are actually pinned to the ground. They are bolted in. That's why you have to be able to move the arm. In the case of Optimus, Optimus is literally a pushover. It's like, get out of my way. He's already having a hard enough time walking as it is. And I'm sure you give him a good shove, he's going to be off of you. So you don't have to worry about that, of being pinned by him, because it's just not going to be an issue for the most case. And, they maybe do some things, because I think some of those joints, probably if the power is off, you will be able to move them. And some of them I think are designed. I think it's the rotational ones you can probably move, but the linear actuators, I think those do break and hold. Yeah. So they're a little bit harder to move. But
again, it's not going to do like a deep knee bend, and so that you're not going to see the thigh and the calf ever contact like this. So it's
not going to do that.
So
right, exactly. And there's going to be some sort of clothing over it to hide any of those things. 'Cause there are some internal pinch points. If you put your finger in where the elbow and the other stuff is in there, you're going to hurt yourself. But as long as you get it covered when the elbow is coming down, you don't have to worry about it breaking everything. And they do something like, the Coke can test with the cobots, that, you put a Coke can in there, and when it's coming around to see if it crushes it or not, it should be able to stop, and you don't want to. And if it is, like, well, okay, that's going to hurt something.
So anyway, I think it's valuable because you talk about cobots a lot, and just for people who might not have understood what they are, they're a very particular type of robot that's designed to interact with humans in a safe way. Unlike the big guys that are behind the barriers.
But they're very slow. They're not going to be able to get the kind of production volume you want, and they're not going to be able to do some of these larger processes. But they can do some smaller things. So they do have their application. They are useful. Otherwise, I think half the robot sales worldwide every year are cobots versus industrial robots.
Interesting. Okay.
Yes. So and the number of brands has exploded. When we were first doing it, we had a much smaller library, and there was like a dozen brands that you knew worldwide. And suddenly, wow, all these were coming in like we'd never heard of. So they just started cropping up because there was consolidation in the robotics in the 80s and 90s, that you ended up with maybe about 10 brands left.
Gotcha.
There was really almost nothing else. And it just looked like, stagnation. Cobots come along, suddenly, new business model.
There's something about making it easier to deal with humans. Okay, so I have class right now. I have to go teach, but I really appreciate you teaching me. This was actually very
fun. Yeah, this is fun.
It was great. So everybody, make sure that you go and follow Going Ballistic 5.
It's Going Ballistic 5. Yeah,
Going Ballistic 5
like an
on Twitter
S.
and the YouTube channel as well. So go ahead and follow Scott. And in the meantime, we will see you in the next video. Bye-bye.